Hello and welcome to our lab on energy. Today we're looking at the energy of a cart rolling down a track. Now this is a low friction cart, and at the top of the track we have a motion sensor. And that motion sensor is going to observe the motion of the cart as it rolls down the track. So as I release this cart, it starts off with a zero velocity. And so that means it has no kinetic energy. But it has a certain gravitational potential energy because it's a certain height off of a reference point, in this case, the tabletop. Now, I'm going to hold my piece of foam down here so the cart doesn't roll off the end of the table. And you can see when I release the cart, it gets lower and lower, so its gravitational potential energy is decreasing, but it gets faster and faster, so its kinetic energy is increasing. Now, if energy is conserved, in other words, there are only conservative forces at work here, like gravity, then the decrease in potential energy is going to equal to the increase in kinetic energy. So the change in potential energy plus the change in kinetic energy is going to equal to zero. And so your total mechanical energy will be unchanged. However, there is a non-conservative force at work here, and that is the force of friction. And so in this case, we will have a change in mechanical energy. And that is equal to the work done by that non-conservative force. So whatever the work done by friction, as the cart travels down the track, the work done by friction decreases the total amount of mechanical energy from the top to the bottom. And you should be able to observe that drop in mechanical energy. Let's look at it from an equation standpoint. Now here you can see the tabletop with the track on an incline. At the top of the track is a motion detector that can view the cart, here's the cart, rolling down the track with increasing velocity. At the end is a foam cushion for the cart to land on. Now, as we said before, there's going to be a change in kinetic energy. And this change in the total kinetic energy, when you add that to the change in gravitational potential energy, that's going to give you the total change in mechanical energy. Now the change in mechanical energy is also equal to the work done by non-conservative forces. So if there is no non-conservative force at work, let's say it's totally gravitational, conservative force, then there's not going to be a change in mechanical energy. That means when you increase your speed, you have to lower your reference point with the ground. So an increase in kinetic energy has to correspond to a decrease in gravitational potential and vice versa in order for the change in mechanical energy to remain zero. However, when you do have a non-conservative force at work, like friction, then the work due to that non-conservative force is equal to the non-conservative force times distance. The distance over which the non-conservative force acts in the same plane that the conservative force is acting. So we're going to sort of see how this works with our experiment. So our dilemma is to acquire data in such a way that we can plot the change in kinetic energy along with the change in gravitational potential energy so that you can see the overall change in mechanical energy, the sum of those two, as the cart moves down the track. If there is a change in the total mechanical energy, that tells us that there must be a non-conservative force at work, which removes some of the energy from the cart from the top of the track to the bottom. So if there's a non-conservative force at work, we're going to end up with less energy at the bottom than we had at the top. So let's take another look at our diagram. Now you see up here the motion sensor at the top of the track, and it's viewing the cart as it rolls down the track. Now as it gets faster and faster, as the velocity increases, then you're going to get an even greater increase in kinetic energy, because kinetic energy equal to 1/2 mass of the cart times the velocity of the cart squared, kinetic energy increases with the square of the velocity. So under a constant acceleration, this velocity is increasing at a constant rate, but kinetic energy is increasing with the square of the velocity. Now gravitational potential energy, we'll call that GPE, is equal to the mass of the cart times G times H, the height of the cart off of the table or off of some predetermined point. Now that height, and I guess I can I'll show you here, this height is decreasing as the cart goes down the track. However, the motion sensor, as it watches the cart go down the track, this distance d is increasing. And so to do this experiment correctly, you've got to set this up so that your distance is decreasing as the cart goes down the track, and we're going to try to correlate that to the height. So one way to do it is to put your cart at the end of the track, go ahead and set it down here at the end, and zero the sensor. Control 0. And what that does is it puts the 0 point out here. Then you go under the data collection menu, or in the Go sensor, and you tell it to reverse directions. And now, instead of reading an increasing distance from the motion sensor, you are reading distance here between this theoretical 0 point as the cart rolls down the track and where the motion sensor is reading. So the distance is no longer there, but it's a decreasing value as the cart goes down the track. So as the cart goes down the track, you see that this is a right triangle, and the distance, or the hypotenuse of this triangle, and theta, if it were given, if you knew the hypotenuse and theta, you would be able to calculate what h is, the height of this triangle as the cart moves down the track. And so now you can do a mathematical transformation of the distance data that you're getting after you zero the cart and then reverse the sensor direction using your software. Now you can do a mathematical transform. And it says that d sine theta is equal to h, the height. So as you can see, it's a pretty straightforward calculation to get the kinetic energy. It's just 1/2 mv squared, and the m, the mass of the cart, is something you can measure with your pan balance, with an offset mass. But getting the gravitational potential energy, mgh, is a little more difficult because you can't directly measure h. However, we've shown that it can correspond to a decreasing distance. You can transform that to a decreasing height using the formula height is equal to d sine theta. You just need, the distance comes from the motion sensor, position versus time graph, but you need theta. Now theta is something, we don't give you a protractor so that you can measure theta. You're going to do that geometrically. And so there's a sort of a meter tape down through here that'll show you the hypotenuse of this triangle that makes theta. And then using your ruler at certain places, you can get a change in height down the track. And if you know the change in height and you know the hypotenuse, you can calculate theta, the angle. One thing to remember though, Logger Pro uses angles in radians, not degrees. So make sure that you state your angle in terms of radians before putting it into your calculated columns. Okay, so now you can see Logger Pro up on the computer screen, and we're going to run this experiment. Now I've already reversed and zeroed the motion sensor, and so we're going to track position versus time along with velocity versus time as the cart goes down the track. You can see velocity versus time is fairly linear, while position versus time looks more quadratic. But now I've also created some calculated columns that's going to show the kinetic energy, which is 1/2 mv squared, and also the potential energy, which is transforms that position to height and multiplies it by mass times gravity, where mass is the mass of the cart. So we'll take a look at our graph when we make those changes. we're going to plot kinetic and potential energy. And so you can see that as kinetic increases, potential energy decreases. Now if I sum those two together, it's going to show me the total mechanical energy. So let me throw that into the graph as well. You're going to be looking at the total mechanical energy of the system. This red line up top. And it's pretty level. So what that shows you is, because that red line is fairly horizontal, not much total mechanical energy was lost due to non-conservative forces. So this is a fairly frictionless track. It does drop a little bit, but not a great appreciable amount. So this almost models a situation where there are no non-conservative forces. Now, to really display the way that non-conservative forces work, we're going to do this experiment again, but this time, instead of using a low friction cart, we're going to use a sliding wooden block. Now you can see that we've inclined the track from a height of 15 centimeters for the cart up to a height of around 40 centimeters here with this block. And I'm going to repeat the experiment. And as I do that, you can see that the kinetic energy doesn't rise nearly as much for that drop off in potential, a greater drop off in potential. And so the mechanical energy in red, you can see it has a much sharper drop off. And so there is a much larger change in mechanical energy now, which shows that the energy was more up here than it was down there. And that loss of energy comes from the work done by the non-conservative force of friction, which was backwards up on the block as it slid down. The last part of this lab is to calculate what that force of friction was. And because the work due to the non-conservative force is equal to the force times distance, well, we can determine how much work was done by the non-conservative force by a decrease in mechanical energy from one point to another. And so between that point and the other, you can also determine a corresponding change in distance as it moved down the track. So now you know between 2 points you can determine the distance and the decrease in mechanical energy. Therefore, you know the work done, you know the distance. You can use work is equal to force times distance to calculate the force of that non-conservative friction that was acting. And so you can use that to determine the frictional force. And knowing the other things, you could determine maybe the coefficient of friction between the cart and the track, or whatever you wanted to determine. So that's how we'll conclude the lab.